let me introduce to you Jens Winkelmann, who was at TCD. You're now in Germany.
Yeah, and I don't work in academia anymore. I work for Vodafone.
Real job. Yeah.
Do something completely different now.
But he's going to give us a reprise of his PhD thesis on columnar structures of sphere.
Yes. So yeah, I'm not working in academia now. I started to work as a data scientist, and I'm just doing this on my holidays now. So yeah, just spent some days in the birthplace. And yeah, for a couple of decades now, scientists from around the world have been studying columnar structures. And in March of this year, Hoki and I actually published the first monograph on this topic, where we summarize the recent development on these remarkable formations. And as all of you should know by now, columnar structures assemble and spheres are being packed densely inside cylinders. And you can see some, oh yeah, this doesn't work. You can see some of these structures in forms of bubbles and balls confined in a tube on the cover of our book. Oh, that should work. Let's see if I can use that.
Got to change slides.
I investigated these structures during my time at Trinity Dublin on supervision from Stefan, and I graduated in 2020. And Hoki and I decided to use the free time during the lockdown of COVID to write a book about the fundamentals and applications of such structures, which essentially is my PhD thesis. So I'm excited to give you a sneak peek into our book in form of this presentation, and I will commence with showing you some or demonstrating you some simple experiment on how you can create these structures yourself by using golf balls, but also show you some reasons why these are interesting to study, and show you some of the results from last decade from Adil, Stefan, Dennis, and me, essentially.
Work history. We just need to click on this.
Yeah, just click here, right? Oops. So this is a very simple experiment on how you can create columnar structures yourself at home. And we actually did this on like a Friday afternoon experiment in Dublin. You just use some
second-hand golf balls collected by Dennis.
Exactly. I think they're fished out of the Irish Sea. And we got a cylindrical tube and painted with some covers essentially, and dropped the golf ball sequentially into this tube. And you can, at the end of the GIF, I overlay it with this contact network, and we'll see later on that we can use it to identify the structures. So these structures are quite interesting because they have diverse appearance on many length scales. Like the largest appearance is probably in botany, and you can have like the corpse flowers, which is like a meter in size, and you have these berries that assemble then around the stem in this ordered structure. I took this second picture here of a cuckoo pint in Dublin. There's a park called Bushy Park where I used to live close by, and that shows you Dublin is just the perfect place to study these structures. Then Stefan is the foams and complex systems group, so you can find them in foams. That's why we studied them in Dublin. These bubbles crystallize to these structures there, and then they are like on a centimeter scale. Then there were scientists from Penn State University who assembled these micro rods by using silicon particles and assembled them inside PDMS pores, and then they formed these also columnar structures, and they made these micro rods out of it. And then in Harvard, they investigated these optical metamaterials. So these are materials with a negative refractive index, and they used nanocolloids that they assembled on the surface of a cylinder. They also created such structures that way. And then there were Brazilian scientists who altered the chemical and physical properties of carbon nanotubes by assembling circular molecules inside the nanotubes. So I think these were like fullerenes that were assembled inside the carbon nanotubes, and that way their chemical and physical properties were actually altered. And while all these structures occur on different contexts and different length scales. They have one thing in common. They're like ordered structures. And who would be a better person to study those structures, ordered structures, than a German? But
Hence the corpse flower, I'm not too familiar with.
Yeah.
What phylotactic structure is that?
I'm not quite sure. It's fairly large. So like
That's why I asked. It's unusual. I mean, the phylotactic structures tend to be rather boring. They're all 2 feet wide or something.
Yeah.
They're all much the same. That looks interesting.
yeah, it's fairly big. I mean, I think the size. So you can see the grid in the background, and I think one of these is like 5 centimeters. So I think the height of this is like a meter.
Wow.
So it's like a really big plant, and you can, I think, where was it? Somewhere in the UK, you can find the flower, and you have to just go in the right time to find this, because I think it's only in like autumn or so, or I'm not quite sure, because you need to get if you go to the wrong time.
Without getting into it, which I declined to do the other day when this arose, I mean, the hexagonal packing on plants, they're not arbitrary, they're a particular family of structures, which people have written endless papers about. But that to me is unusual. I'd like to follow that up. Thank you.
All right. So yeah, but this diverse appearance, or this common ordered structures in this diverse range of length scales actually allows us to use just one type of simulation essentially to study them all, and we use like this very generic approach where we just minimize the minimize like an energy or an enthalpy function to find these structures. In this presentation, I want to cover two different methods of how you can arrange these or assemble these structures. The one is what I would call the old-fashioned way, or like the orthodox way of just packing spheres inside cylinders. But there was also a novel method created by a group in Korea, in South Korea, around Lee et al., and they used rapid rotations to create these structures. And I will talk about this in the second part. And then at the end, I'll talk about, I wouldn't call it future work, because that's work that has also been already done. There's some work from Stefan, and also some work that I did, like I started during my PhD. I want to cover that in the last section. So let's start with the traditional way of creating columnar structures by packing spheres and cylinders. So the simplest, or one way to one parameter to tune these structures is the diameter ratio. So this is the ratio of tube diameter to sphere diameter. If you have a fairly small diameter ratio, you get just the zigzag structure. You have your tube diameter to sphere diameter is fairly small, then you get like the zigzag structure, and then when you increase it, you get these more complex structures, and we use these phylotactic notations to label them. And these phylotactic notations are essentially describe the number of spheres that you get along a certain crystallographic direction. But here we just use them essentially to label the structures, to identify or categorize the different structures. That's mainly what we use them here. It originates in botany, so it originally comes from botany, this notation, and I have a very nice description of it actually in our book if you want to dive into that. So yeah, these structures that I present here have all like a certain symmetry. That's why we call them uniform structures, and we'll later see, I think Hoki already mentioned there's also like line slips, and we later see what the difference between these two structures are. So the way we can simulate the different ways to simulate it. And one of the easiest ways is by using hard spheres. So these are spheres that do not overlap. So they're always like a certain distance d apart. And there are essentially three main methods to simulate these structures. The first one is done by Adil, I think already like 10 years ago it started, where you simulated annealing. And it's a heuristic method to find the optimum of a certain loss function. And it actually turns out that I just used this method on Tuesday at my new work at Vodafone to find the minimum or to find the optimum of a certain loss function. You have like a wide range of application here. So what Adil did, correct me if I'm wrong, Adil, you run it at a fixed cylinder length and a cylinder diameter and cylinder length, and then you sort of check out different cylinder diameters and different cylinder length, and then you just check for the structure that has the energy of closest to zero, and the one with that when you order them essentially by length, and the one with the shortest length will give you the lowest density packing, right?
Yeah, so I start off with a cylinder with a fixed diameter, and I keep a very short length to begin with, a certain number of spheres, n number of spheres. Then I run the simulated annealing and see how low I can get the energy to be. And then I just let the cylinder slightly, run it all again, and see how low I can get the energy to be, and then keep lefting until the energy just drops to zero. And then that is pretty much a situation where the spheres are just touching each other or just slightly overlapping. That's my hard sphere limit, basically.
Yep. And then Hoki already talked about sequential depositioning, and that's essentially the golf ball experiment, just made into a simulation that you drop your golf balls or you drop your spheres into a cylinder, and then you sort of optimize the cylinder length during each or after each drop to find the optimal structure. And these were like the two methods up until 2016 that got you like the optimal packings up to like at least the simulated annealing got you the packing up to like a diameter ratio of 2.7 until a guy from the US came along with a linear programming method. So this is Charbonneur's work. He used a method called linear programming. And linear programming usually works that you want to optimize a certain loss function under subject to certain constraints. So he essentially set the loss function to the cylinder length, and he says that my constraints are essentially hard spheres. This is like the constraints that we are using. And then
how did they search amongst all the alternative structures?
So
there must be lots of alternative structures. I mean, I never understood Charbonneur's paper how they
managed to find the global minimum, right? Like why you didn't stuck in global minimum is kind of the question, right? I don't know how they ensure that they find the best structure.
I mean, they obviously did, but I never understood the paper how they.
Yeah, because usually you would think that sequential that this linear programming will lead you into local minima and not global minima. But I don't understand. Yeah, I'm not quite sure why that is. I know that they use a trick to then. So when they find one optimal structure, they use this one essentially. So they sequentially put this as initial condition into the next structure. I know they do that, and that probably helps. But you would still think that they will find they will go from a local minimum, or essentially they at some point should go into a local minimum. So I'm not quite sure. They might have run it like really for like lots of cases and then just pick the minimum out of that. That's the only guess that I have. And then one property that we already talked about a lot is the packing fraction or the packing density. And what Avila did during his paper from 11 years ago is he looked at the packing fraction versus the diameter ratio. And we can identify now these uniform structures that I mentioned before at these peaks of this curve. And you'll find the intermediate structures between these peaks are called a line slip structure. So essentially, all these structures either consist of a uniform structure or a line slip structure. If you think about like hard spheres, they're very rare to find in nature. Most material that you find in nature is like squishy, deformable, like the bubbles that we studied in Dublin. So a better approach to this might be to look at soft spheres. And we use here this old Turing model where you just assume that that spheres can overlap, but when they overlap, essentially their energy behaves like a spring between them. So the energy goes up with the overlap squared. And then we use these soft spheres and we just put them into a cylinder of a certain length L and a diameter capital D. And we use image spheres here above and below that are like twisted by a certain twist angle to simulate an infinite column. And what we do then is we minimize the enthalpy of the system. So the enthalpy is essentially calculated by the inner energy of the system plus a regularization term of pressure times volume. And we minimize then this enthalpy with respect to the sphere positions, the length of the cylinder, and the twist angle. And there are two ways essentially to minimize this. One would be to look at local minimal structures, and then you wouldn't find like the best structures. You wouldn't find the structures with the best or with the lowest density. You'd find instead you'll find metastable structures, and you can like study metastability and also hysteresis. And you can also use global minimization algorithms. So you could use simulated annealing here again. But we also figured out during my PhD that there's a method called basin hopping, and I think the method was actually developed by somebody here, wasn't it? Like we talked to somebody here when I visited last time.
And uses it, but we can.
I don't think he.
It's David Wales.
Yeah.
Yeah.
Did he invent this? No.
I think David Weiss, but also somebody else. I can look up the reference.
Yeah, I remember we talked to somebody here about this method, and they were like, "Yeah, you can it's very easy. You can just program it yourself." I'm just using a library method, which makes my life so much easier. But yeah, we use this essentially to find now the global minimum structures, and we do this now to map out a phase diagram. And
But there is no potential between the particles and the walls.
So they behave the same. So if they overlap with the walls,
So
you have again the energy goes up with the overlap to the wall squared. Yeah. So yeah, we mapped out a phase diagram, and I do call it a phase diagram. I don't work in academia anymore. I don't have to worry about any reviewers. But yes, we do borrow a couple of terms here from thermodynamics actually. So phase diagram, we use the term enthalpy. Because it kind of like fits the definition of enthalpy, but we do not have a thermodynamic system. So we do not have like particles that are moving. We do not have any thermal. Actually, we do not have any temperatures or so in our system. We still use these terms because they sort of fit. And like what we call a phase here would actually be a certain structure, like a region in this phase diagram. And you also have like these structural transitions, which you also can compare to like a thermodynamic transition. And you can also have then these continuous transitions or like a discontinuous transition, which is also very similar to what you see in thermodynamics. So that's the reason why we like to borrow these terms like phase diagrams, for instance. So there is a good argument to use the term phase diagram because you have lots of similarities to thermodynamics. And yeah, so this is the phase diagram. We have here the pressure P on the y-axis and the diameter ratio D on the x-axis. And we actually, so increasing the pressure essentially means you're making the sphere softer. So we actually have the hard sphere limit at p equals 0, and we actually managed to reproduce all of Adil's structure from his hard sphere simulations. And these are like these 10 uniform structures and the 14 line slip structures. And what we noticed in this phase diagram is that these line slip structures all vanish with increasing pressure. So the softer you make the system, the more the line slips actually vanish. Unfortunately, we do not find any like new types of structures in this diagram appearing with higher pressures, but we do essentially predict the line slip structures for sort of low pressures, and that essentially made us wonder, like, there is a prediction for line slip structures in a soft sphere system at the limit to like going to hard sphere system, and we wondered if you can actually create this in an experiment. But before I go into any experimental details here, I want to explain to you what a uniform structure is and what a line slip structure is. So when you look at a uniform structure, this would be an example of a uniform structure, the 3-to-1 uniform structure. You can look at the contact network first. So you just turn every contact into a line and every sphere into a dot in this diagram. And you already noticed that the neighborhood of each sphere looks identical. They all have like 6 neighboring contacts. And then you can like take this contact network and you roll it out in a plane, and you get this this nice hexagonal lattice that we already also saw in Hauke's presentation. And yeah, so for each sphere, the neighborhood looks identical, and that's the reason why we call them a uniform structure. You can do the same then for a line slip. So this is an example of a line slip. I'm not sure if you can see it, but there are like gaps opening up here. It gets much easier to see when you just look at the contact network. And again, each dot is a sphere and each line is a contact. And you actually notice there's a loss of contact right there, for instance. And then you can do the same again. You can roll it out in a plane, and you get this sort of pattern where you can see that the gaps actually happen along a line. And when you move these spheres along these lines, actually when you shear it along these lines, you'll get back into it like a uniform structure. And that's why we decided to call it a line slip structure, because you sort of, when it's like the spheres are being slit compared to the uniform structure. And I find these structures very remarkable because this gap is sort of adjustable with the pressure or the compression of the system. So if you like change the pressure of the system, you can like adjust how much this loss of contact actually is. So that's like a range of what this or like how big this loss of contact is. And this, like, I still think there could be like applications in like material science by looking into materials where you can like change stiffness, conductivity, or also what's it called, like the resonance frequency or something like this of one of those rods. And you have those rods, and you can vary these properties by just adjusting the compression or the pressure of the system. So far we predict them in our simulations, and then the question is, when you predict them, can you also find them in an experiment? So that was already like 6 years ago, I think. We decided to go into the lab and put this to a test, and we did this very nice experiment where we just put bubbles inside a tube, and then we added liquid from the top, like water from the top, and made the structure more wet. So that way you get closer to the hard sphere limit, essentially, because you make the spheres more round. And we actually noticed that there were like gaps opening up, and we took pictures of it, and we compared it then to the simulation of a 3-to-1 line slip structure. And you can actually see how these gaps correspond very well to the gaps that you can see in this in the simulation. So we were actually the first one to ever find a line slip structure in a soft sphere system by using bubbles in a glass tube. And but the problem is this phase diagram and the phase diagram only provides you like the ground state structures. It doesn't give you like the full picture of what your structures can do and like what structures you actually get. And it completely neglects like metastable structures, like because all these local minima that you can run into, you completely neglect them. You only look at the global minimum. That's the only thing that that interests you in the phase diagram. But if you think about like a real life experiment, if you want to compare your theory or your simulation to like a real life experiment, the real life experiment would run a bit different. You would it would be very unlikely that you directly run into a ground state structure. You would probably end up in like a metastable structure, and this could be, for instance, a 3-to-1 structure. And then you start changing one of these parameters like the pressure or the diameter ratio, and then you can transform the structure into a different structure. So, for instance, you could go from the 3-to-1 into the 4-to-2 by increasing the diameter ratio, and then when you revert this whole thing and you decrease the diameter ratio again, you'll actually get back into the 3-to-1 structure, but this might occur at a different pressure or a different diameter ratio. And essentially what you observe then is hysteresis. So hysteresis is essentially the effect of it's the effect that your structure that you're in actually depends on the structural history of the system. So, for instance, if you increase and decrease your diameter ratio, and the transition points are at different positions, then that actually means you'll see hysteresis. And the way you can then investigate this is by looking at stability diagrams. So these are then not really phase diagrams, but very close to that. Instead of showing where the ground states of the different phases are observable, you show where a certain structure is stable under from certain history. And so you display essentially the region of metastability for these structures. And we did a little video of this. So in the center of this, you can actually see one of these stability diagrams for a 3-to-1 to 4-to-2 transition. And we'll follow along this thought here now. So if I play the movie, this thought we will first increase the diameter ratio, and then we revert it and decrease the diameter ratio again. And here you'll see the contact network, and here you actually see the actual packing. Oops, go back. So when we increase the diameter ratio, we'll actually jump into a line slip structure for a short time between these two blue lines. And when we revert it and we decrease the diameter ratio again, we'll notice that it's skipping the line slip completely and it actually jumps back to the 3-to-1 structure at the red line. So the positions, the transitional positions, or the regions where we transition into these structures are different or depend on the history of the system.
Okay. Can you remind me how the pressure is normalized? I mean, what does 0.01 mean?
Oh gosh, yeah, pressure. Yeah, I need to look into that again. It's been too long. I don't know how we normalized it in some way. I don't remember how.
Maybe it's defined in the book.
Yeah. I think it is, but I need to look into that. As I don't really remember how we normalized it. It's because it's in the simulation. It's just the
Lagrange multiplier of the. It's a Lagrange multiplier of the.
Yeah, but it's I can't quite remember the length scale in there, which is the sphere diameter, and there is supposed to be some other. I can't remember. There's some other physical parameter in there. Yeah. From that, you can construct the pressure.
Yeah.
Yeah, because you have a spring constant as well.
No, right. I mean, there's a nominal energy scale.
That's an energy scale, yes.
Yeah. So it must be like energy over like volume or something like this. Yeah. So yes, the transition that we looked at is the 3-to-1 to 4-to-2 structure. And we noticed that we can go from 3 to 1 to 4 to 2 over a line step, and then we can go back, and we just see it at the transition at a different point. So this is what I would call a reversible transition. But you can also actually observe irreversible transitions. So if you continue to increase the diameter ratio from the 4 to 2, you will eventually end up over the line step in the 5-3-2 structure. But if you now decrease the diameter ratio again, you will not get into the 4 to 2, back into the 4 to 2. You'll actually get into the 4-3-1 structure, which is a completely new structure, or like a different structure now. And this would be then a irreversible structure. But now if you continue to decrease the diameter ratio from the 4-3-1 structure, you will get into the 3-3-0 structure. And eventually you can, if you continue to decrease, you'll get into this 3-2-1 structure. So essentially you will see like a cyclic pattern where you can only rotate through in a clockwise manner. And I actually recorded the enthalpy for this cycle by using my simulation, my soft sphere simulation. You can see here we start in the 3-to-1 structure. We increase our diameter ratio. We follow the blue line here, which is the enthalpy curve, and we'll end up in the 4-to-2 structure. We continue to do this. We go into the 5-to-2 structure, and when I'm in this structure, at some point I revert this. I decrease my diameter ratio again, and I'll end up first in the 4-3-1 structure, but eventually I get back into the 3-to-1 structure, and actually do this at a very low pressure, so I get a very small enthalpy, and I essentially do this in the hard sphere region. I actually noticed that there's a completely different context, completely different field, where you can see very similar diagrams to this, and that's the context of compressing and decompressing origami structures. This was a paper from Karen Daniels. So they investigated the compression and decompression of these origami structures and the hysteresis and the and memory behavior of such structures by using the Price-up model. And they get similar diagrams here. And these systems are actually quite similar in the sense that both are like quasi-dimensional, and you both compress and decompress them, and that way you'll see similar effects and similar diagrams. And they were interested in these in this because they were looking at so-called mechanical metamaterials. So these are materials that are supposed to store information and memorize information on a certain structure, and they could be used for building reprogrammable structure. That was their idea. So I think this similarity could actually end up like opening a new type of new type of research questions for these columnar structures. So one question would, for instance, be: can you also apply this Price-up model actually to our columnar structure, and what does that actually give you? And they observe what's called return point memory. So you can like you'll cycle through these diagrams, and you can like return to like your at some point you return to your previous structure, and that way like it remembers memorizes the previous structures. And then last but not least, the question would be: can you actually find amongst our common structure any candidates for these mechanical metamaterials that they are interested in? And this similarity and this research question actually got me a free trip to North Carolina last year. I was in the US anyway for a wedding, so I decided to drop by Karen Daniels' lab and visited her. I gave the same presentation eventually, although the trip wasn't quite free for me because she made me work in the lab. And if you know me, I don't like
not something that Dave normally wants to do.
But we recorded a very nice video on. We use these. Oh, come on. We use these these hydrogen spheres, they're essentially like spheres that you use to water your plants, and they're like one centimeter in diameter, and the tube is then like 2 centimeters in diameter. And we put them into this tube, and we use like a washer and a screw. Like it's a very dirty experiment. It's not very clean. You can see there's a washer, there's a screw, and then we compress the system. Oh gosh. We compress the system slowly, and you can see at some point the structure goes from a chiral structure into an achiral structure. We continue to compress it a bit, and then we decompress it. And you'll notice that I think at this point here we were transitioning before, but now it's still in the 4-2 structure in this achiral structure, and now you can see it's transitioning back into the previous structure. And when you observe this closely, you can actually see that the chirality of the initial structure does not agree with chirality with the final structure. So it actually changes it's the same structure at the beginning and the end, but it has a different chirality. And yeah, we just did this in one day, essentially. It was just a very quick and dirty experiment, but you could obviously use this setup to investigate our stability diagrams in more detail, or investigate the history of these structures in more detail that way.
I just want to make sure, because there are two phenomena. There's hysteresis, which I thought I saw. I couldn't actually see the hand of this change. But could you do it one more time? Because I want to see, because I thought hysteresis also, the path back didn't seem to be time symmetric, regardless of whether you reverse time.
Yeah.
Also give your first hand, it's PT symmetry that you got there be done. Because it looked like it's not time reverse.
Yeah, but I also, so with the time, be careful. I also like played around with the
which you're decompressing.
yeah, this is one thing, and also the video. I obviously, because this video took like 2 minutes to record or so, and I wanted to fit it into like 30 seconds.
I ruined that.
Sorry, I've got a question. If you do your compression sort of very, very slowly, or aesthetically, will you achieve the same results?
That would be the hope, I guess. But yeah, so this system differs a bit from the system that I studied with my simulations. I want to redo this with my simulations at some point, but I only have like a certain amount of time to do this. So this one is, you compress the system to actually make the volume smaller. But in my system, I change the pressure, right? I don't change the volume, so the volume can be adjusted during every minimization step. But I could adjust my simulation by doing exactly that. It would take some effort and time to do that.
So it looked to me like when the thing was, you were expanding back, it wasn't, the structure sort of there was something happening on one end that wasn't, like it was sort of unwinding from one end rather than uniformly across both.
Yeah, because the way the screw works is like so you don't want to, you want to have it go in a certain speed, right? And to ensure this, we had like a screw, so that's the reason why it was turning. But yeah, that could have an effect on the chirality.
I mean, one would expect it to be like in the optimal situation be sort of uniform in some sense across the whole cylinder, right? So this, rather than having, it looked like there was different structure one end than the other.
What else there was like
Yes. There's at some point I think you'll get a mixture of these two structures.
But that wouldn't be theoretically all.
What do you mean by?
Well, wouldn't the optimal, whatever measure one uses for that, be, one would expect or not, that it be uniform across the whole?
Not necessarily. I only have like 5 minutes left.
I'm sorry. I just kind of
we gave you extra time.
Because
You started late.
huh?
You started late.
So you get extra time.
All right. So in my second part, actually, we investigate, or you can find structures that are like binary mixtures of two, that you don't always find homogeneous structures. You can also find binary mixtures. not quite sure if I have time to cover this. I might have to speed up a bit in that part. But yeah, you do sometimes you are able to see mixtures sometimes. That is a possibility, and I think I would expect to see mixtures here as well. Yeah, but yeah, I think if you run simulations, you can actually try to find them.
I'd like to follow with you afterwards.
All right. So yeah, a while back, this topic was given a new spin by a group from South Korea, Lee et al., and they used a method that involves rapid rotations to find these columnar structures. And let's just dive into their video. So they have also a nice video on how they create these structures. So you can see these. They use like polymeric beads, so they put them into water. So the polymeric beads actually have a lower density than the water, and that way they're being pushed towards the center, and then they form these columnar structures right here. And
is this a rubbish video? Speed it up.
Now tell how fast is the running.
So they're running it at like 3,000 RPM, and they use a high-speed camera to record this. We actually did similar experiments in Dublin. We also bought the lathe and we did similar experiments. We didn't get a high-speed camera. We got a strobe light, and we just matched the strobe light to the rotational speed, and that way you can also make the structure visible, which is a much nicer, much cheaper approach, let's say it this way.
This answers the question of you last dinner last night.
I told you not to keep telling people about it.
No, I not to say more. I just realized you didn't know about the price.
So let's look at the mechanics, what's happening in this experiment first. So they place these spheres, and the spheres have a lower density than the surrounding fluid, and that way the fluid is being pushed outwards and the spheres are being pushed inwards. So essentially, if you leave the system alone, if you don't rotate it, the spheres would just float on top of the water. And what you see here is essentially that there's a centripetal force pushing the spheres towards the center, and the centripetal force is proportional to the distance r, and then you have a rotational energy that goes with the distance r squared, and they then observe these homogeneous structures at certain rotational speed and number density, or these binary mixtures. So you can actually see here there's an interface between these two structures, and so yeah, you do sometimes see these binary mixtures.
Just like the diameter is different. At least on the top.
Yeah. So that's because you're not confining it with like hard walls or anything. You're confining it with this rotational, this r squared potential, right? You have like a energy potential that's actually.
The spheres are not contacting the cylinder.
Yes. Yes.
That's the.
Yes. They're just confined by the rotation essentially. So eventually we decided to, so they've done the experiment, and we decided then to do like analytic energy calculations for these structures, but using soft spheres. So in the experiment, they had like hard spheres. They used these polymeric beads. They were essentially hard spheres, but we used then soft spheres. And we do this essentially in two steps. First, we calculate the energy for the homogeneous structures, and the energy is simply the rotational energy plus the soft sphere interaction term. And the soft sphere interaction term can actually be reduced to just a structural constant, and that way the energy of this system is just the rotational energy, and it's just dependent on r squared. And that means you can find the structure of these structures by just minimizing with the minimizing the total energy of the system just with respect to the radial distance, just with like one parameter. And then you can find.
Does that argument depend on the potential between spheres being harmonic, or does that work for?
Yes, you have again the soft sphere,
Yeah, but if you had a Hertzian contact or something, would it work the same way?
Ooh, not quite sure. I would say so, because that would only be, because that's only like, I would say yes, because it's because there would only be like the context between the spheres, and it's and it would just be, so you reduce everything to just this, the entire interaction between the spheres is only reduced to like a structural constant, and it only the entire your entire structure sort of only depends on the radial distance. So it's like sort of breathing, can like go bigger or smaller. That would be the idea behind this method, at least. And then the binary mixture, I have to say the infinite binary mixture is constructed with this Maxwell construction, or also known as common tangent construction. So what you do here, assume this is your homogeneous structure, like two homogeneous structures, and then the binary mixture is the common tangent between these two curves, and then in this region you will find your binary mixture of these two homogeneous structures. And you can calculate now the energies versus the inverse number density, and then all your homogeneous structures are these, the energies of the homogeneous structures are these colored curves, and the energies of the binary mixtures are the black solid lines. And then we'll observe the homogeneous structures only in the region of these colored regions, and the binary mixtures are observed in the white regions. And then you can extend this essentially also. So this is at a constant rotational speed, but now you can do this at various rotational speed, and that way you can again create a phase diagram, which I will again call a phase diagram, because again, all these colors represent a certain phase or structure. And then we have here inverse number density again on the x-axis and the rotational speed on the y-axis. And we'll see in general that these these homogeneous structures, or the regions of the homogeneous structures, are increasing with the increasing rotational speed. But at 2 points, or two structures actually vanish in a certain point, which are called paratectoid points. So at these points, these homogeneous structures vanish together with the binary mixture, and there's a new binary mixture above them that consists of the adjacent homogeneous structures. And then at rotational speed of 0, you'll sort of encounter again the hard sphere limit. What I mean by...
Yes, can I just make a general point that may be interesting? Very general point that this work demonstrates, I'm talking about the wider context of this work, it demonstrates a lot of things that are taught in material science courses. But to my knowledge, there's no good demonstration of those effects, and they have to be applied with great, or investigated with great care in many different alloy systems, for instance, in metallurgy. I'm not aware of good systems where you can think about them and maybe do experiments like this as part of the educational system. There may be a value there.
Oh, I see. Yeah, with the, especially with the lathe, right? You just bring the lathe and demonstrate the different types of transitions. So yeah, the particular transitions and this kind of stuff is something that we borrowed from metallurgy, essentially. But yeah, in the at low rotational speed, or at 0 rotational speed. So if you think about it, obviously 0 rotational speed would mean the system is not turning. Yeah, about 3 minutes. We can recover the hard sphere limit, and I think yeah, I'll skip this real quick. So let's talk about some other work that I started in my PhD, and that Stefan and Dennis continue with their current PhD students. So so we bought the lathe essentially, and we decided to look at chains of spheres in a line. So if the number of spheres is commensurate with the length of this tube, you just get a line of spheres. When you now start to compress this system, they actually start to buckle. And we essentially investigated this buckling behavior, and it's quite interesting to see. I mean, you can nicely see that this buckling actually happens exactly in a plane. It's now like, it's still a three-dimensional system, but the buckling only happens in a plane. And we investigated this with experiments, with simulations, I think, and also with the theory that we developed. But I sort of forgot what the theory was all about. That's why I'm not presenting this in detail here. But it's in the book. There's a whole chapter on this in the book if you want to read on this. And so far, like all the research that we've done is essentially investigate how you assemble these structures and what are the assembly methods. And we studied the assembly method, and we understand this quite well now. But I'd like to actually to move this into a more applicable region. And to do this, you could do this by looking into more material properties. And Hoki started to do this actually. He showed you a bit before on the electrical conductivity. That's he mentioned this in his talk before, where he essentially used Kirchhoff's law. So he abstracted the packing into like a diagram of resistors and just resistors that are connected with each other. And then he calculated using Kirchhoff's law the conductivity. You could do the same actually by thinking of the spheres as inductors and the contacts are like capacitors. And then you could like calculate the resonance frequency. So then you have like an LC circuit, and you can calculate the resonance frequency. And that could be interesting for studying these optimal metamaterial or any like photonic crystals essentially. And then there was also been some work on photonic crystals and the polarization band gaps by Hoki.
Yes, maybe I can say something about it. I didn't mention it in my previous talk because our paper is still under.
Okay.
but we've just got this resubmitted yesterday, so maybe now I can say something. So basically,
cut out the word face.
And so we basically consider these columnar of spheres, but we consider a sort of a hexagonal packing of this. So we have the columns of spheres. We have columns of these spheres packed in a hexagonal manner. And by doing this and by choosing a particular chirality of these structures, we have numerically found that there's a certain degree of circular dimorphism for such structures, which make these structures as potential candidates for photonic crystals. So that's what we have done so far.
Yeah, and I think that's all to say to the possible application to this in like material science. And last but not least, I want to acknowledge and I want to certainly thank Adil, Stefan, and Dennis for the support during my PhD. And as you might know, the book is dedicated to these three because they introduced us to these packing problems. Yeah, that's Adil catching a fish. So I just leave you with the.
Remember that?
Yeah. Thank you very much.
Maybe just one comment. Jens showed the string of particles that were rotating with a tiny zigzag pattern in the center. So we continued to work on that, as you indicated, derived the whole theory, a continuum description of these types of patterns. So there was a publication for that. So
can I just also comment briefly that this research benefited from being very poorly funded. And it was not meticulously planned in advance, and it staggered extraordinarily from one discovery to the next in closely related fields. There might be a moral in that.
Maybe one more remark that comes to mind when looking at
the hydrogel spheres in the tube and this, the presence of both chiralities, right? Yes. Simultaneously. There was work a few years ago on elastic ribbons that transition under certain conditions, which I don't remember, from one chirality to another with the structure that separates the two. I think people call it perversion. And I'm wondering if that's a continuum analog to what you're seeing there.
Could be, yeah.
The subject for coffee.
Yes. Yeah. Thank you very much, Jens.